Suppose I have M pigeons and N pigeonholes. Well, it's kind of a bit of a pain to draw pigeonholes. So, what I'm going to do instead is to draw boxes, specifically pigeon boxes. So, the pigeons, well, we can use little dots like this, colored dots. These are my pigeons. And we'll draw little squares for the boxes. These are my pigeon boxes. Now I'm going to put the pigeons into the boxes and see what happens. As you probably know, the pigeonhole theorem or principle works like this. Let's say I've got the boxes. Let's say I have 4 boxes. And let's say I have 1, 2, 3, 4, 5. So M is 5 and N, number of boxes, is 4. In this case, I have M is greater than N. And when I have M is greater than N, well, if I try putting my pigeons 1, 2, 3, 4, 5, well, one box is going to have more than one pigeons. So when the number of pigeons exceeds the number of boxes, at least one box must have more than one pigeon. Now, you may think, okay, this is like really simple. Does this even need to be proved? Can we even prove something like this? Sometimes it's like super hard to prove something so simple, like, proving 1 + 1 is 2. There's a rumor that Alfred North Whitehead and Bertrand Russell took hundreds of pages to get around to proving 1 + 1 is 2. I don't know. I've never read the book, so I don't know how true that is. But that's a story. That's an interesting story. But like, this is one of those things you think, well, this is like really simple. How do I prove this? Do I even need to prove it? Can this be proved? Like, you can tell me, okay, this is a very clear principle. More if I have more pigeons than the number of boxes, yeah, sure, one box is going to have more than one. That's obvious. Okay, it doesn't need to be proved. We can take that as an axiom or principle. I'm cool with that. However, what if somebody says to you, well, can this be proved? Because in fact, Dirichlet used this. He was a great mathematician, and he used a principle like this to prove some very non-trivial results in number theory. His principle that he used is a kind of super version of the pigeonhole principle. I will eventually get around to talking about it and do some applications of it to problems. But for now, let's consider the simplest possible case, which is this one. You just have M pigeons and N boxes. Okay, and we try to prove this. And if we can prove this, well, then maybe we're all set for examining, the more advanced version which Dirichlet himself employed. Right. So what I'm going to do is follow a very clever proof that I have seen some time ago. And this involves the following idea. We're going to look at the maximum number of pigeons in a box. So what we have is, for example, we have box 1, we have box 2, and so on, and some box somewhere in the middle. Then finally we have box n, and somewhere in the middle we have a box with the most number of pigeons. Let's say in this case 3. All right, this box has 1, this box has none, this box, let's say, has 1. So x star, the maximum number of pigeons, is this box here, let's say the kth box. Now, if you have more than one box, which is maximum, that's no problem. Just choose one of them. Okay, now the next thing we're going to look at is the average. Now, the average is the sum of all the pigeons in every box. So this is, call this x1, the number of pigeons in box 1, x2, number of pigeons in box 2. This is xk, number of pigeons in box k, which happens to be the maximum by our assumption. And here xn is 1, number of pigeons in box n. So we're going to add all of these up, xn, divide by n to get the average. But this is actually equal to m over n, and that's very important. We want to remember this. All right, that this is actually equal to m over n. We want to remember that. So our first task, which will take us very far, very close to where we want to be, we want to prove the following. We want to prove that the max number of pigeons in a box is always greater than or equal to the average. This seems obvious, like many things, It seems obvious, but then if you have to prove it, it's not obvious. Like in this case, you might argue and say, yeah, this is all totally obvious because it's such a simple situation like we have here. Sure, but Dirichlet's original idea is more complex than this and not so easy to claim that it's obvious, and we'll get to that in another video. It's very, very interesting to look at the more advanced versions of the pigeonhole principle. So let's get used to this and try to prove it in a rigorous way so that we have some tools to tackle later on, more advanced version. All right, so what does this mean? Let's see. Okay, so we want to prove this here. We want to prove this here. Now, proving something like this, you say to yourself, well, how do I prove this? I have no idea what to do. And I agree. I mean, if you gave me this problem cold and if I never saw anything about it before, yeah, I'd be stumped. But I have this idea that I always keep in mind, and that's when you're totally stumped, when you don't know what to do, when you have no clue how to approach a problem, then use contradiction. If you know about contradiction, that's great. Okay, we're going to use it right now, and we'll use it in future videos coming up soon. But if you don't know about contradiction, don't panic. I'm going to do videos about it. Later on, it's coming. You can watch them out of order. Okay, but you'll see how it works. Just watch some examples. It'll gradually you'll learn it by osmosis. So what we do in contradiction, we assume that something is false. So we're gonna say this is not true, and that's going to lead us to some hopeless contradiction that we have to get out of it. So we'll have no choice but to claim, okay, it must be true, because if it's not true, we get into these absurd contradictions and our whole mathematical world collapses. So I'll show you a great example of this right now. So we're going to take this and we're going to say it's false. So x star is actually is actually less than x average. So the opposite statement of greater than or equal to is less than. Just think about that logically. It's just a question of logical thinking. And we're going to assume that this is true, and we're going to see that this causes our whole world to collapse. And so it had better not be true. Okay, so let's write this out carefully. What we have here is x star is less than x1 plus x2 plus dot 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 up to xn over n. That's the average. And let's move this over. X star, nx star is less than x1 plus x2 plus all the way up to xn. And we can expand this. N times something is the sum of n terms of that thing. So x star plus x star plus dot 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 plus x star. And there's n of these terms, n terms. And this is less than x1 plus x2 plus dot 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 xn. Now, I'm sure you're looking at this right now and you're saying to yourself, well, this already looks impossible, because we said here that the maximum, x star is the maximum. That means it's greater than or equal to every other box. Like x star is the number of pigeons in the box that has the most pigeons. And so what we know is this, that x star is greater than or equal to xj, where j is any box, because that's the definition of maximum. It has to be bigger than or equal to any other box. So this follows from the definition of maximum. And so what we have here is, if I replace each one of these with x1, x2, x3, that's even less. So I have x1 plus x2 plus all the way up to xn. And this is going to be less than or equal to x star plus dot 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 x star. Do you see why? Again, let's look here. X star is greater than every other box. So this greater than this greater than this greater than this one. And this is strict inequality, x1 plus x2. And so this sum is actually m, and this sum is m. When we add up all the pigeons in the boxes, we have m. So what we have here, don't be misled by this. Okay, this is not the issue. You know, m can be less than or equal to m. That's okay. This is the problem. M cannot be strictly less than m. So what we have here is m is strictly less than m. And whoa, our whole mathematical world will collapse. If we have something like this, like something like 1 is less than 1, boom, the whole mathematical universe just gets sucked into a black hole of nonsense. So since we can't allow that, we have to assume that this thing we said is true is actually false. So therefore, it's the other way around. X star must be greater than or equal to X bar. Very beautiful proof. It's so simple, it's actually deceptive. It's deceptively simple. All right, we did it. We're almost there. We proved that the maximum is greater than the average. Very good. And now let's go back here. I said that this thing is quite useful here. Remember this? Let's put a nice highlight on it. So X bar is m over n. And now keep that in mind, please, because what happens when m is greater than n? So the pigeons are greater than the boxes. What happens? Well, X bar, the average, is going to be m over n, but this is greater than 1. So in this case, this implies X star, the maximum inside a box, the maximum number of pigeons inside a box, has to be greater than 1. Because this is greater than or equal to m over n, but this is greater than 1. So again, we have this trick that you have to keep in mind. This is a non-strict inequality, but this one is strict. And, in some ways, as we will see over, many videos, you're going to get the idea that a lot of mathematics actually depends on a distinction between greater than and greater than or equal. I know it sounds like a very trivial thing, but you can make a good argument that a lot of analysis is based on this difference between these two things. So this has to be always you have to be very careful about logical thinking here. Yes, this can be equal to m over n, but m over n is strictly greater than 1, and therefore x star, the maximum, is strictly greater than 1. So therefore, there is a box. There is a box, the max box, which has more than one pigeon. And there we go. A beautiful theorem, and the proof is beautiful because you're proving something that seems to be absolutely trivial. Like it seems to be intuitively obvious. So it's actually amazing that there exists a rigorous mathematical proof for something like that. But we need it. We need it because we're going to use these ideas to talk about Dirichlet's more advanced forms of the pigeonhole principle later on. So I hope you like this video. So if you do like this video, hang on, click like, okay, and subscribe to my channel so that I can continue to make more videos. You can encourage me, cheer me on, and thank you for being with me for this video, and I will see you next time.